the work energy theorem and its application. So at this point, we are now ready to discuss one of the fundamental um, like theory or conservation law. Sorry, it's a law. It's a conservation law in physics, which is the conservation of energy. But before going to the conservation of energy, there is something that we have to understand about the conservative forces, since we will only be dealing with the conservation of energy for these kind of forces. Now, for a force to be considered as a conservative, um, that has two specific requirements. The first requirement is whenever that force is doing work, that work must be path independent. So I want you to focus your attention on the illustration over here. So for example, a conservative force does work from in moving an object from point A up until point B. Now, if that if that force is indeed a conservative force, if for instance it took this path 1, that means it moves horizontally towards the left and then going down, and then the other path would be it moves from point A going down and then going horizontally to the left, or simply it took the path of the lesser distance from point A to B, that one over there. If it is truly a conservative force that is doing that work, the work done by this, I will call that work 1, work 2, work 3, they should be all equal, okay? Regardless of the path that it took if it's a conservative force. Now, what does this implies for our class? So for your level of physics na klase, this is quite abstract, and for all practical purposes, wala kayo ni siya implication yun class. More like this is a conceptual thing that you need to understand whenever we talk of conservative forces. Kay dili man ta mag-deal with the conservation of energy kung naay non-conservative. So probably that's for your next na physics grade level. Okay? So kung na ako, if for instance, if I make another path, let's say, if this is a stair from B to A, no, and then I have this path over here, like the conventional stair, regardless of that path, as long as I am moving from B to A, or ganina A to B man to siya, wala na siya mag-matter. The work will still be the same kini sa akong stairs dire or katong murag ramp na shortcut. If that work is, the force that is doing that work is a conservative force. So this is the first condition. The second condition for a force to be considered as a conservative force is that that force must be dependent only upon the distance. So it must only depend on the distance r and not with the velocity. That means to say that when you try to inspect, or simply speaking, when you try to inspect the equation that dictates, or that dictates the behavior of that force, you should only see a dependence upon r and not with v. And that is true for both of these common conservative forces that you keep on encountering in class. For example, the first case of gravity, upon inspection of the equation that defines it, you notice gm1 m2, this term over here is just a constant. So the f of g is dependent on this quantity 1 over r squared. And that is r, walay v. So that means it's conservative. Now, the same case with your electrostatic force, k, q1, q2 is just a constant. So your F sub E, your electric force, is proportional, or is a function of R and not with V. Hence, your electrostatic force is also a conservative na force. On the other hand, your friction over here is not a conservative force. That is why we notice that whenever a ball is moving over a floor with a friction, we notice that eventually it slows down because some of that energy of the ball is actually being converted to like dissipating heat over the contact of the surface. So friction is not conservative also, in the sense that it is dependent upon velocity. So you could model your friction as F is equal to some constant B multiplied by your velocity. So that shows dependence of that force, friction force, over the velocity. And whenever that is the behavior of your force, where it depends on velocity and not with r anymore, then that is a non-conservative na force. So the basic idea of the conservation of energy is that consider these balls over here. Basically they are the same ball. It's just denoted a different position in time. So that's ball A, and this is still ball A, or just have it as ball B. But I just want to make it clear that they are not different ball. They are the same ball. It's just that they are in different position at different times. Now the conservation of energy basically is is telling you that all of the energies, the sum of all the energies over here. And by the way, when we say the sum of all the energies, specifically in this discussion, I am talking about the mechanical energy, which is, again, the mechanical energy is just the sum of your potential and kinetic energy. So the conservation of energy, in the sense that it's conserved, is whatever the sum of your energy at point A, that is also the sum of all the energies at point B. And again, that is the mechanical energy, or simply the sum of potential and kinetic. So to make it clear, I would illustrate it in this manner, that the potential energy at point A plus the kinetic energy at point A is equal to, let's say, some 100 joules. So this is just for the sake of illustration. So since that energy is conserved, because we are dealing with a conservative force, the only force, if you remember, acting on this one, assuming there is no air resistance, is the force of gravity, which is a conservative force. So going back over here, the potential energy also at point B plus the kinetic energy at point B must also be 100 joules. Okay, so that is a consequence of your or basically that is just what the conservation of energy means in this case. So if I made some points or intermediate point over here, and I call that point C, and then for the sake of discussion, I add a point here, and I call that point D. As you would expect, according to the conservation of energy, when you take the sum of the potential energy at point C, and then you add also the kinetic energy at that point, you should also get 100 joules. And the same arguments goes for point D. So if you take the potential energy at D, add the kinetic energy at D, you should be getting 100 joules. Okay. So basically, the energy here is conserved because the force acting is a conservative force. Okay, so that would be very different if there is a non-conservative force. For example, for this falling ball, if you have friction, then that would be very different. The energy would not be conserved in this manner at all. Okay. So another thing for you to visualize before we deal with a problem over here is this one. So assume that, I know this is very ideal and not realistic, but for the sake of discussion, let's just stick to this one. If you have a roller coaster and then it has some loop over there and some second loop, I know it should be perfect circle, but yeah, I will just try to make it perfect circle. That and circle over here. Okay, it's not working. Maybe some circle over here. Okay, it's not working. Let's try it a third time. Okay, good. And then another one, you have this, assume that it's flat. Okay, let's try my best. Okay, and then another circle over here. Okay, should be flat over there. Okay, that's one. Yep. Okay, at this point, I'm going to name some point A. By the way, the assigning of points is really something that you should by now realize to be important. Point C, point D, and point E. Now, I will ask you of this question. Assuming that there is only the work of gravity here, and the only force acting is gravity and no friction. I know this is not realistic, but for the sake of discussion, assuming that is true, what are the energies at points A, B, C, and D, and E? If the energy at, let's say, point A is a 1000 joules. So you try to answer that one. So you should answer, the correct answer is, they should have the same energy, okay, regardless of the points that you are talking about, because basically this hypothetical setup over here and hypothetical energy of 1,000 joules is the same or is conserved over the system. All right. But as you can see, firstly, I have the freedom to set my h is equal to 0, right? So for the sake of this discussion, and I find it somehow easier to set my h is equal to 0 on the ground. So if I will set this as my h is equal to 0, I know for sure that point A has the highest potential energy, right? So point A, the energy at point A are U at A and the kinetic energy at A. All right. But you realize at point A, we're still dealing with the case of point A, that the kinetic energy at point A must be 0. Why it's a 0? Because that is initially at rest there before going down. But all of that energy, that 1,000 joule of energy, is concentrated on its potential energy. Okay? So another one, when we try to move down, so syempre that object will move over here. So it's gaining velocity. And then, or it's gaining speed, as you could say. At point B here, over here at point B, I think it's clear to you now, or hopefully it is, that at point B, the energy potential all is 0 because that is where you set your height, plus the kinetic energy at point B. Now, the kinetic energy at point B, since you noted that all of the potential is 0, the 1,000 joules energy is all kinetic. That means to say at this point, it is very fast, moving very fast. All right? Then as your object over here tries to move up, for example, in this path, it tried to move up, and you know that it's already gaining height. So, kay height diri it tried to it tries to gain some height, and in that case, your potential energy is also rising from 0. So at this point, your potential at C is no longer 0 because it has some height h over there relative to the ground, plus the kinetic energy at point C. Now, as you would expect, the kinetic energy at point C compared to point B is slightly lesser. It's because your 1,000 joule of energy is no longer entirely kinetic, but you have your potential now. So for example, let's just say for discussion, if your kinetic energy in that case is 500 joules, if ever this is 500 joules, then the potential energy must also be 500 joules. Why? Because the sum of the potential and the kinetic energy, which we call mechanical energy, is conserved. And that means to say that the entire, I don't know why I wrote A here. This is ME. The entire mechanical energy over this path should always be 100 joules. That's why both of these quantity adjusted to 500, 500. Alright, so I'm hoping this is making sense. So the next video will be solving. I think we have 3 problems on solving an application of this concept. So the first one is this, which is we will solve it the way, the conservation of energy, and your grade 8 physics, which is what's this, kinematics equation. The second one is this problem, and the last one is this problem. Okay, so I am hoping you find time in trying to understand this concept